Good evening, sir.
Good evening. We'll soon start. Okay, so let's start our discussion today. So let's proceed with the first problem of this session.
Hello everyone. In this video, I shall discuss the solution of question number 9 of GATE Physics 2016. This is a numerical answer type question. The entropy S of a system of n spins which may align either in the upward or in the downward direction is given by S equal to minus kb into n into p log p plus 1 minus p into log 1 minus p. Here kb is the Boltzmann constant. The probability of alignment in the upward direction is p. We need to find out the value of p at which the entropy is maximum. Let's solve this question. In this question, we have S equal to minus n kb into p log p plus 1 minus p into log 1 minus p. For the maximum value of entropy, we have ds dp equal to 0, which means ddp of p log p plus 1 minus p into log 1 minus p equal to 0. After differentiating, we get log p plus p by p minus log 1 minus p minus 1 minus p by 1 minus p equal to 0. So log p plus 1 minus log 1 minus p minus 1 equal to 0. So log p is equal to log 1 minus p. This means p is equal to 1 minus p. So 2 into p is equal to 1, or p is equal to half. So for p equal to zero point 0.5, the entropy is maximum. So in this question, the correct answer is 0.5.
Is there any question? Hello, am I audible? Hello, am I audible?
Yes, sir.
Is there any question or doubt from
No,
this?
sir.
Okay. So I am repeating it again, the solution from the PDF. Okay. So I am sharing the screen. So this was the question. So here, what is entropy is? So S equal to minus n into kb into p log p plus 1 minus p into log 1 minus p. So this is the definition of entropy. This is already given to you. Okay? And you have to find out the value of p for which the entropy is maximum. So how to do that? For that you have to just differentiate the entropy with respect to p and set it to 0. Okay, so that's very simple. So if you differentiate the entropy with respect to p, then you get log p minus log 1 minus p equal to 0, or p equal to 1 minus p. This means 2p is equal to 1, or p is equal to half, or zero point 0.5. So for p equal to 0.5, the entropy is maximum, right? So here p can take values between 0 and 1, right? Because this is some probability. So let's plot is as a function of p. Then what will happen? For p equal to 0, what happens? Let's check. For p equal to 0, log of 0 So this is undefined, but here p equal to 0. So this term is 0, okay, because p is 0. And at p equal to 0, the second term becomes log 1, right? So log 1 is 0. So for p equal to 0, s is 0. Okay. Now what happens when p is equal to 1? When p is equal to 1, then the first term becomes log 1, which is 0. So when p is equal to 1, the first term is 0. And what happens to the second term? 1 minus p becomes 0 when p is equal to 1. So the second term is 0 when p is equal to 1, and first term is also 0 because log of 1 is 0. So for both p equal to 0 and p equal to 1, s is equal to 0. So the range of p is between 0 and 1, and for p equal to 0, s is 0, and for p equal to 1, s is also 0, and for p equal to 0.5, s is maximum. But what is the value of this maximum? Let's find out. Let's see what happens if p is equal to half. Then it will be equal to minus in kb log half, or in kb log 2. So s by n kb, if we plot it with as a function of p, then it will be like this. This is clear? Hello?
Yes, sir. Yeah.
Okay. So this question is complete now. So the plot of entropy as a function of p will look like this, and for p equal to half, the entropy becomes maximum and is equal to in kb log 2. Okay. Okay. So let's proceed with the second question.
Hello everyone. In this video, I shall discuss the solution of question number 11 of GATE Physics 2016. This is a numerical answer type question. N atoms of an ideal gas are enclosed in a container of volume V. The volume of the container is changed to 4V while keeping the total energy constant. We need to find out the change of entropy of the gas in the units of Nkb log 2. Let's solve this question. In this problem, the total energy of the ideal gas is constant. It means temperature of the ideal gas is constant during this process. So it is an isothermal process. The change of entropy delta S is equal to integral del Q by T. Here del Q is equal to dE plus P dV. As the total energy is constant, we have dE equal to 0. So delta S is equal to integral P dV by T. Now for n atoms of an ideal gas, we have PV equal to n kBT. So P by T is equal to n kB by V. So delta S is equal to integral dV into n kB by V. After integrating, we obtain that the change of entropy is equal to n kB log V2 by V1, where V2 is the final volume and V1 is the initial volume. In this problem, we have V1 equal to V and V2 equal to 4V. So delta S is equal to n kB log 4. Now 4 can be written as 2 square. So the change of entropy is equal to 2 into n kB into log 2. So the change of entropy of the gas in the units of n kB into log 2 is 2. So in this question, 2 is the correct answer.
Am I audible?
Yes, sir.
So in this question, there are ideal gas particles, gas atoms, okay, and they are enclosed in a container of volume V, and the volume of the container is changed to 4V while keeping the total energy constant. Okay, and you have to find out the change of entropy of the gas. So total energy of the gas is constant. It means the temperature is constant. So the process is isothermal process. But how do you know that the total energy is constant, is equivalent to that uh, temperature
3
is
by 2
also
kBT.
right? So from the equipartition of energy, you know that per degree of freedom or per unit degree of freedom, we have the energy equal to half kBT. Okay, and let's say there are n number of particles. Okay? And degrees of freedom of individual particles is F. Okay, so the total energy is equal to this thing, right?
Yes, sir.
So if you calculate specific heat, then it will be this thing, right? But it's not important in our problem. In our problem, it is important to remember that E is proportional to T. This holds only for ideal gas particle, right? So here the total energy is constant. It means the temperature is also constant because temperature is proportional to total energy, right? So temperature is constant. It means the process is isothermal process. Okay. Now, what is the change of entropy? This is the definition of the change of entropy, right? Integral del Q by T. Here del Q is the imperfect differential. This I have discussed in previous class. And what is del Q? From the first law of thermodynamics, we know that del Q is equal to dE plus del W. Okay, del W is the amount of work done by the gas. Here it is equal to PdV for gaseous system, right? And so the change of entropy is equal to integral dE plus PdV by T. Okay, and in this problem the total energy is constant. It means there is no change of total energy, so dE is equal to 0 in this problem. Okay? So this problem is now very simple. Delta S is equal to integral PdV by T. Now we know for ideal gas PV equal to N kBT. This is the equation of state of ideal gas, right? And what is P by T? P by T is equal to N kB by V. So just replace P by T with N kB by V here. Okay? And the limits of this integral over volume will be V1 and V2, and V1 is the initial volume and V2 is the final volume, right? And after integrating you get delta S is equal to nkb log V2 by V1. So in this problem the initial volume V1 is equal to V, and V2 the final volume is equal to 4V, right? So just put the values in this expression, then you will get delta S equal to nkb log 4. Okay. Now this 4 can be written as 2 square, so this can also be written as delta S equal to 2 into nkb into log 2. Now you have to find out the change of entropy in the units of nkb log 2. Okay, so in that unit the value is 2, so the answer of this question is 2. So 2 is the correct answer for this question. Okay, clear? Any
Yes,
question or
sir.
doubt?
No.
Okay, fine. So if there is no question, let's proceed with the third problem of this live session.
Hello everyone. In this video, I shall discuss the solution of question number 49 of GATE Physics 2018. This is a numerical answer type question. A microcanonical ensemble consists of 12 atoms with each taking either energy 0 state or energy epsilon state. Both states are non-degenerate. If the total energy of this ensemble is 4 epsilon, then we need to find out the entropy. Let's assume that the number of atoms with energy 0 is n1 and the number of atoms with energy epsilon is n2. We have total 12 atoms. So n1 plus n2 equal to 12, and the total energy of the ensemble is 4 epsilon. So we have 0 into n1 plus epsilon into n2 equal to 4 epsilon. So n2 is equal to 4. Thus n1 is equal to 12 minus n2 equal to 8. So the number of microstates of this ensemble is equal to 12 factorial by 8 factorial into 4 factorial. Now this 12 factorial can be written as 12 into 11 into 10 into 9 into 8 factorial, and the value of 4 factorial is 24. After some simplification, find that the total number of microstates is equal to 495. So the entropy is given by Kb log omega. Here omega is equal to 495. So the entropy is equal to Kb log 495. Log of 495 is approximately equal to 6.2. So the entropy is equal to 6.2 kb. So in this question, the correct answer is 6.2.
So am I audible? Hello?
Yes, sir. Yeah.
Okay. So in this question we had 12 atoms. A microcanonical ensemble consists of 12 atoms, with each taking either 0 state or the energy epsilon state. So each atom can occupy any one of the two possible energy states with energies 0 and epsilon, right? And the states are non-degenerate, just simple 0 state or epsilon state, no degeneracy is there. Okay, if the total energy of the ensemble is 4 epsilon, then we have to find out the entropy up to 1 decimal place. Okay, so how to solve this problem? So let's first consider that number of atoms with energy 0 is n1 and the number of atoms with energy epsilon is n2. Okay, and there are total 12 atoms, right? So n1 plus n2 must be equal to 12, right? And the total energy of the ensemble is 4 epsilon. Okay, so there are n1 number of atoms with energy 0 and n2 number of atoms with energy epsilon. So what is the total energy? will be equal to 0
N1
into
epsilon.
n1 plus n2 into epsilon, right? So which is equal to n2 into epsilon, and this is equal to 4 epsilon as given in this problem. Okay, so n2 is equal to 4 in our problem. This means n1 is equal to 12 minus n2, and n2 is equal to 4, so n1 is equal to 8, right? So we have n1 equal to 8 and n2 equal to 4. Okay, so this there are 12 atoms. These 12 atoms can be arranged in 12 factorial number of ways, right? And among these 12 atoms, there are 4 atoms which are in the level with energy epsilon, and there are rest 8 atoms which are in the level with energy 0, right? So this 8 atoms with energy 0 and the 12 atoms, sorry, the 4 atoms with energy epsilon are identical, right? So we have to divide the number of microstates by 8 factorial and 4 factorial respectively. Okay, so the total number of microstates will be equal to 12 factorial by 8 factorial into 4 factorial. So after, if you do some simplification, then after doing some simplification, then you get this number of microstates omega is equal to 495. Okay, and entropy is given by kb log omega, where omega is the number of microstates, and here it is equal to 495. So entropy is equal to kb log 495, and which is approximately equal to 6.2 kb. So in this question, the correct answer is 6.2. Okay, so any question or doubt here?
Sir, in this question we have considered the particle to be distinguishable. So why do we use the particle are distinguishable? The atoms are similar.
Sorry,
Uh,
can you
in
repeat
this
your question?
in this we have considered the particle as a distinguishable and apply the formula for mic number of microstate. So why we do that?
So let's say there are 12 atoms. Okay, and how many ways you can arrange them? 12 factorial, right?
So
Here,
the when we consider the atoms as distinguishable, then we have arranged the in that way. But it does not mention the
right.
atoms are
Hmm.
indistinguishable. Actually.
So just consider 12 atoms. Okay, and you can arrange them in 12 factorial number of ways. So if they are identical atoms, okay, and then among these 12 atoms, there are 8 atoms which are in the level with energy 0, so they may look identical. So you have to divide the total number of ways by 8 factorial. Okay, and similarly there are 4 atoms with energy epsilon, and they also look similar or identical. So you have to divide again the total number of ways in which you can arrange them by 4 factorial. Okay, that's all. I think now it's clear. So if there is no other question from this, then let's proceed with the next problem. Hello, someone has raised hand. Any question?
Sir, by mistake.
Sorry?
By mistake.
Oh, okay, okay, fine.
Hello everyone. In this video, I shall discuss the solution of question number 51 of GATE Physics 2019. This is a numerical answer type question. Consider two systems A and B, each having two distinguishable particles. In both the systems, each particle can exist in states with energies 0, 1, 2, and 3 units with equal probability. The total energy of the combined system is 5 units. Assuming that the system A has energy 3 units and the system B has energy 2 units, the entropy of the combined system is Kb log lambda. We need to find out the value of lambda. Let's solve this question. Let's first consider system A. There are two particles in system A and the particles are distinguishable. We denote them with different symbols. We denote the first particle like this and we denote the second particle like this. There are four energy levels with energies 0, 1, 2 and 3 units. The system A has energy 3 units. We can place the first particle with energy 1 unit and the second particle with energy 2 units. We can also place the first particle with energy 2 units and the second particle with energy 1 unit. We can also place the first particle with energy 0 unit and the second particle with energy 3 units. We can also place the first particle with energy 3 units and the second particle with energy 0 unit. So there are four possible microstates in which the system A has energy 3 units. Now let's consider the system B. System B has energy 2 units and the system B also consists of two distinguishable particles. We can place the first particle with energy 0 unit and the second particle with energy 2 units. We can also place the first particle with energy 2 units and the second particle with energy 0 unit. We can also place both the particles with energy 1 unit. So there are three possible microstates in which the system B has energy 2 units. So the total number of microstates of the combined system in which the total energy of the combined system is 5 units is equal to omega A into omega B, which is equal to 4 into 3. So the total number of microstates of the combined system is 12. Now the entropy of the combined system is equal to Kb log omega, which is equal to Kb log 12. In this question, it has been given that entropy is equal to Kb log lambda. So we have lambda equal to 12. So in this question, the value of lambda is 12. So 12 is the correct answer in this question.
Am I audible? Hello.
Yes, yes, sir.
So in this question, there are two systems, A and B. And both the systems have two distinguishable particles. Okay? And in both the systems, each particle can exist in states with energies 0, 1, 2, and 3 units with equal probability. The total energy of the combined system is 5 units, and the system A has energy 3 units, and the system B has energy 2 units. Okay, and the entropy of the combined system is kb log lambda. We have to find out the value of lambda. So basically we have to find out the entropy of the combined system. Okay, so let's first consider the system A. So system A has two particles, and the particles are distinguishable. So we denote the first particle with this dot and particle 2 with cross. Okay, and the energy levels are like this 0, 1, 2, 3. Okay, so the total energy of system A is 3 units. It is given in the problem. So how to do that? I mean, how to arrange the two particles such that the total energy of system A will be 3 units. So we can do it very simply. There are many ways to do that. In one way, we can place the first particle with energy 1 unit and the second particle with energy 2 units. And we can also do the opposite thing. I mean, you can place the first particle with energy 2 units and the second particle with energy 1 unit. Okay, so we have found two possible configurations, and there may be some other configurations also. Let's see. We can also place the first particle with energy 0 unit and the second particle with energy 3 units. As you can do it, then we can do it the opposite way, because energy will remain same in that way also. So I mean, you place the first particle with energy 3 units also, and the second particle with energy 0 unit. So these are the possible ways in which the total energy of subsystem system A is 3 units. Okay, so we have found there are 4 possible microstates. So omega A is 4. Now for system B, what happens? The energy is 2 units. Again, there are two particles, and we denote them as before. We denote the first particle with dot and second particle with cross, as they are distinguishable, right? So in this case, you can place the first particle with energy 0 unit and the second particle with energy 2 units. Also, you can place the first particle with energy 2 units and the second particle with energy 0 units. But there is another possibility that you can place both the particles with energy 1 unit. Okay, you can do that. So there are 3 possible microstates in which the energy of the system B is 2 units. So omega B is 3. So how to find out the total number of microstates of the combined system? So this is equal to omega A into omega B. Now how it is omega A into omega B? Then you have to look into the additivity property of entropy. I will come to that later. Okay, so here omega A is 4 and omega B is 3. So just multiply them, then you will get the total number of microstates of the combined system is equal to 12, such that the total energy of the system will be 5 units. Combined system will be 5 units. Okay, so entropy of the combined system is given by kb log omega. The entropy is given by kb log omega, and here omega is equal to 12. So entropy is equal to kb log 12. In this question, it is given that entropy is equal to kb log lambda. So the value of lambda is 12. That's very simple. So 12 is the correct answer. But there is one point in this question. Sorry. So this omega is the number of microstates of the combined system. Okay, and this is equal to omega A times omega B. Now take log on both sides. So on the right hand side it will be equal to log omega A plus log omega B. Now also multiply kb on both sides. So this is the definition of entropy, right? S equal to kb log omega, and this is this kb log omega A is equal to SA, the entropy of system A, and similarly SB is the entropy of system B, where SB is equal to kb log omega B, right? So this is the additivity property of entropy. Now in this question you can also do it in different way. I mean, you have found that omega A is equal to 4 and omega B is equal to 3. So from this you can calculate SA and SB. So SA is equal to KB log 4 and SB is equal to KB log omega B, and omega B is 3. So SB is equal to KB log 3. So SA plus SB is equal to S, the total entropy. So we have S equal to KB into log 4 plus log 3. So log 4 plus log 3 can be written as log of 4 into 3. Just using property of logarithm function. Okay. So this is equal to KB log 12 and S is equal to KB log lambda. So lambda is again 12. Just another way to solve this problem. Okay. Actually these are same. I'm telling it in different way, but these two are same. Any question from this?
No, sir.
I think I have shown this equivalence in one class. This is equal to kb log omega and is equal to this definition is by kb equal to okay. I have shown this equivalence, right?
Yes, sir.
Okay. So this equivalence is valid only for large n limit, right? This is clear why large n limit is important.
No, sir. Can you explain?
Sorry. Oh,
Can you
so
explain?
okay, okay, right. I'm going to explain it now. Okay. Let's say there are n particles. Okay. Among them, n up are the number of particles which have spin oriented in the upward direction, right? And n down is the number of particles with the spins oriented in the downward direction, right? And n is the total number of particles. Then what will be the value of this omega? It will be simple n factorial by n up factorial into n down factorial, right? Hello.
Yes, sir. Yeah.
Okay. So now calculate s. S is given by kb log omega, and omega is equal to n factorial by n up factorial and down factorial. Now I'll use Starling approximation. What's that?
ln factorial is equal to n ln n minus n.
This I will write as n log l log n minus n. But this approximation is valid only for large n. Okay. That's why I was telling that large n limit is important for this equivalence. Okay. So as I am explaining, let's take 2-3 minutes. I will solve. I will. I will prove the equivalence again for you. So what is log n factorial then? Using Stirling approximation, this is equal to this thing. Similarly, I will assume that this n up and n down are also large. Okay, then I will again use Stirling approximation for n up and n down respectively. Okay. Okay. Now n up plus n down is equal to n, the total number of particles. So these terms cancel out. Now this n can be written as n up plus n down, right? So this step is clear. Last line, yes or no? I
Yes
am
sir,
just
yes sir.
written n equal to n up plus n down. That's all. Nothing else. Okay. Now let's take n up common. Then it will be this. This is again clear. Just very simple algebra. Nothing else.
Yes sir.
Now I take common this n common. Okay. Then we'll get s equal to minus n kb into n up by n log n up by n plus n down by n log n down by n. So now what is n up by n? This is the probability of finding the particle with spin up, right? So this is equal to n up by n equal to p up. Okay, this is the probability that a spin is found with upward direction. Okay, in the upward direction. Okay, similarly n down by n equal to p down. Now we have this thing, n up plus n down equal to n, or n up by n plus n down by n equal to 1. This means p up plus p down equal to 1. So this is indicating that the sum of the total probabilities is equal to 1, and Here you just use this formula. And here what is P down? P down is equal to 1 minus P up. So this can again be written like this, is equal to NKB P up log P up plus 1 minus P up log 1 minus again P up. Okay, so this is the equation we have seen in the first problem of our live in this live session, right? Yes.
Yes, sir.
Okay, and we have plotted it as a function of, plotted the entropy as a function of P, also P up. It will be like this for P equal to 0 and 1, entropy 0, and for P equal to 0.5, this is maximum. Okay, so this we have derived explicitly. So clear, or any question here?
Sir, there is another derivation in which we haven't assumed large number of molecule n. Can you explain?
There is any
Ln
other,
derivation for this
but
formula.
this is valid only in large n limit, right?
Yes, sir.
Otherwise this will not hold, because in statistical mechanics, you know, there are large number of things and you have to take ensemble average kind of thing.
Okay.
Okay, any other question?
No, sir.
Anyone else? Okay, if there is no question, then we'll stop here today. And
Sir, can you share PDF?
PDF, I have not found anything, any way to share that.
Sir, Google Drive.
Google Drive, okay, but how to share the link with you?
Mm,
Is there any way? Can you suggest any way?
I don't know.
I also don't know. So anyway, the videos will be available in the portal. It may take some time, but it will be available. I mean, the individual videos. I mean, let's say I have solved 4 questions, right, today.
Yes, sir.
These 4 questions will be separately available after some days. Okay, with question number. You have to just search the question number and see the video. And you may pause, take notes, whatever. That will be helpful, I think, for you.
Sir, can you mail PDF?
But mm, I think the students are changing every day. I mean, let's say some people are coming today, next day some other people will come. So there's no fixed mailing list, right? So that I can share everyone.
They are limited student 9, 10.
So I think in attachment I can share you. Let me see. If we have time today. Okay, I can do it. Mm, I can share the link of the Google Drive where I am presenting. Okay, that link I can give you. Okay.
Okay, sir.
Okay, so on the next day, I'll give you the link of the first 8 week video. Okay, up to
Sir,
today.
you can type in chat box, share in
Right, right.
chat box.
That's what I am saying. Next week I will do that. These
Okay,
videos are not visible to all right now. I have to change the settings and I'll do that. Next week I'll
okay, sir.
surely do it. Okay. And on the next week we'll start our discussion on classical mechanics. Next we'll discuss Lagrangian dynamics, and the week after that we'll discuss about Hamiltonian dynamics, Poisson bracket, canonical transformation, etc. Okay, so let's stop here today. Thanks everyone for joining. Thank
Thank you,
you all.
sir.
Thank you.
Good night.
Good night. Bye.
Bye.